So in this video we will solve a problem that is related to matrix chain multiplication. The problem may be given as given four matrices P, Q, R and S. The dimensions are also given 10 cross 20, 20 into 50, 50 cross 1 and 1 cross 100. And the order is P into Q, Q into R, R into S, because maintaining the row column or even column row relationship, that is for P total number of column is 20 and for Q total number of row is 20. So you can move on for P into Q in this order. So similarly Q into R, R into S can also be possible. So you have to find the optimal sequence for the computation of multiplication operation. Or the problem can be represented in other ways, where the matrices will not be given, their dimension sequence will be given. That means find the optimal parenthesization of a matrix chain product whose sequence of dimension is 10, 20, 50, 1, 100. The same problem but different representations. In the first case the total number of matrices are given, but the second case only the dimension sequence is given. From the dimension sequence you can easily calculate the number of matrices present in the chain. Here total 5 dimensions are given, 20, 10, 20, 50, 1 and 100. So total number of dimension minus 1 is the total number of matrices. So normally we call it as dimension dot length minus 1 equals to the total number of matrices. Here 5 dimensions are given, so 4 matrices are present in the chain. The same problem with different representation. We will apply matrix chain multiplication algorithm using dynamic programming approach to solve this problem. And the necessary formula, which we have already derived in our last class, that is m of ij equals to 0 if I equals to j. M is a table which will be used to store the cost of multiplications, and here in this case we are less bothered about the product generated, rather we are interested in the cost of multiplication. So actually it is called the scalar multiplication, and our main objective is to find out the minimum cost. So that's why it is written as minimum of m of ik plus m of k plus 1 comma j p plus p of I minus 1 into p of k into p of j if I less than j. That means in this table of m of ij we will use only the upper triangular half. And what would be the probable value of k? K starts from I and repeat up to j minus 1. That's why it is less than j. And actually we need two tables to solve this problem. One table is displayed here, that is m in the formula. One for storing cost and another for records which index of k achieve the optimal cost in computing m of ij. So if you follow my first lecture on matrix chain multiplication algorithm, so where you will find out how to derive this formula, that we have already told. So we shall use the table S to construct an optimal solution. So along with M there will be another table. So using S, that means the second table, you can find out the optimal solution. That means you will find out the parenthesized sequence. That means in this chain there are 4 matrices where the parenthesis should be given. From S, that means from second table, you can identify it. So now proceeding for solutions of the problem. I am making this video only because of students of EC asked me to make it, because we discussed in the last class about the algorithm and formula, how the formula is derived, along with one sample problem. But for better understanding or even for permanent document, so whenever they can have a good network connectivity, they can go for it. So for this they ask for the video recordings of the solution, so that's why I have built it. So m of ij, this is the formula. So my advice to follow this guideline to solve this problem. Actually we need two tables. One is for m and second one is of s. Then your question will be, what will be the dimensions? Dimension will be n cross n, where n is the total number of matrices in the chain. So in this problem there are 4 matrices in the chain. So M table will be 4 cross 4 and S table will also be 4 cross 4. And not all parts will be used. I less than j part will be used. That means the upper triangular half of both the matrices will be used. Okay. And both the matrices means M and S table actually. I am talking about these two tables actually. So I is the row index of the table and j is the column index. For M, row index starts from 1 and ends at n because it is n cross n table I told, and column index also starts from 1 and repeat up to n. That means j also starts from 1 and repeat up to n. That is same for S also. So if it is a 4 cross 4 table, so definitely row starts from 1 and repeat up to and ends at 4, and j starts from 1 and ends at 4. Simple. So now, as we have the formula that is M of ij equals to 0 provide I equals to j, and the other part, so for our calculation we will note down some steps which I derived from the formula actually. So for taking the short time to solve the problem. So actually the formula is represented here in 3 steps totally. One is when for I equals to 1 up to n, where n is the total number of matrices, M of I comma I equals to 0. This is actually the first part in the formula. When I equals to j, M of ij stores 0 actually. So I equals to j means you can write here I comma I because I equals to j. So this is represented as, for I equals to 1 to n, you store M of I equals to 0. Then the second you can go for I equals to 1 up to n minus 1. Then M of I comma I plus 1 is basically the scalar multiplications only, that is pi minus 1 into pi plus 1. If you go through the derivations of the formula which I have discussed in the last class, you will find this extraction actually. And in that case, S of I comma I plus 1 will receive the value of I. So this will play the role like k. And the third one for others, that means for other cells, M of ij will use the formula, that is minimum of this one, where k starts from I and repeat up to j minus 1, and I less than j always holds. And in that case, S of ij will receive k, for which you can get the optimal cost. That means this k achieved the optimal cost in computing M of ij. So my advice to note these 3 and go for solving the problem. For I equals to 1 to n, M of I equals to 0. For I equals to 1 to n minus 1, M of I comma I plus 1 will be calculated using this formula. When I equals to 1, 1 comma 2, when I equals to 2, 2, 3, then I equals to 3, 3, 4, like this. For others, you can apply this formula and get the result. So now, this is our problem. I have 4 matrices, P, Q, R, S, the dimensions are given, and you know the dimension sequence is indicated by the parameter P. For the first one, it starts from P0, P0 into P1, P1 common, P1 into P2, P2 common, P2 into P3, P3 common, P3 into P4. So this was given like the other approaches of the same problem. That means when dimension sequences are given, that means P0 equals to 10, P1 equals to 20, P2 equals to 50, P3 equals to 1, and P4 equals to 100. So if the dimensions are given, I told you total number of dimension minus 1 is the number of matrices in the chain, and here the chain is explicitly given, total 4 matrices are shown. So n equals to 4 here. So I have to construct 2 tables, I told, because I need to have the 2 tables. Both of them will be n cross n by nature, and row index starts from 1, column index also starts from 1. So the same approach is applied here. So M will be 4 cross 4, S will be 4 cross 4, I is the row count and J is the column count. I starts from 1 and repeat up to n means 4, J starts from 1 and repeat up to n means 4, and the same construction is for S. Okay, then I have to fill up the table. So as per the formula is stated here, that the first case when I equals to 1 to n, let me construct one by one. I equals to 1 to n, here I have 4 matrices in the chain. So this I already told n equals to 4. So in this formula I will be 1 up to 4. Then in that case m of I comma I equals to 0. So this is the dimension sequence I wrote here again. So I have these two tables. I have filled up because I have already calculated it. So first one, I equals to 1 to n, that means I is 1 to 4. M of I equals to 0, that means m of 1 1. Then when I equals to 2, m of 2 2, m of 3 3, m of 4 4, all will be 0. So the principal diagonal of m table are filled up by 0. Okay, then come to the second formula. I equals to 1 up to n minus 1. Then m of I comma I plus 1 is calculated using the formula, that is pi minus 1 into pi plus 1. So now here I equals to 1 to n minus 1 means I equals to 1 to 4 minus 1, because n is 4 here. I have 4 matrices P, Q, R and S, or I have 5 dimensions, so total matrices is 5 minus 1, 4. So 4 minus 1, here it is 3, because I equals to 1 up to n minus 1 is the second formula. That is, in that case, for this combination I have m of I comma I plus 1 equals to this formula, and s of I comma I plus 1 will receive that I value. Okay, so when I equals to 1, so it will be I comma I plus 1 means m of 1 comma 2. When I equals to 2, it will be m of 2 comma 3. When I equals to 3, it will be m of 3 comma 4, I plus 1. So you apply the formula pi minus 1 pi plus 1, that means I is 1, so pi minus 1 means p0 into p1 into p2. So as per the data is given, p0 is 10, p1 is 20, p2 is 50, p3 is 1 and p4 is 100. So I have applied it. So 10 into 20 into 50, that is 10,000, and s of I comma I plus 1 will receives the value of I. Here I is 1 and s of I, that means 1 comma I plus 1, that is 2. Actually you are calculating m of 1 2, and at the same time you have to calculate s of 1 2. So s of 1 2 will receive I. When I equals to 1, that means 1. So we have filled up m of 1 2 equals to 10,000, and at the same time s of 1 2 will be filled up by 1. Similarly, when I equals to 2, because you have to repeat up to 3 na, I equals to 1 up to 3. So when I equals to 2, it will be m of I comma I plus 1, that means m of 2 comma 2 plus 1, that is m of 2 3 we are going to calculate. So formula is pi minus 1 into pi plus 1, that is p1 into p2 into p3, because I equals to 2 is starts from I minus 1, so p2 minus 1, that is p1 into p of I into p of I plus 1, that is p1 into p2 into p3. So it is by the data, that is the calculation, so it is 1000. And at the same time s of 2 3, s of 2 3 will receive the value of I, that is 2. So I stored 1000 here, m of 2 3, and s of 2 3 receives 2. And similarly when I equals to 3, I calculate m of 3 4, because I plus 1, so it will be started from p of I minus 1, that is p2, p of I, that is p3, p of I plus 1, that is p4. You calculate it, you get the 5000 as a value, and at the same time s of 3 4 will receive the value of I, that is 3. So it will play the role like k in the formula. So it is 5000, it is 3. Up to this we have covered it. Then the formula suggests for rest you have to apply this one. M of ij equals to minimum of this one, which is the actual formula, with the boundary of k starts from I up to j minus 1, and s of ij will receive that k value for which you are getting m of ij as minimum. So first of all, whenever I have to calculate the remaining, I have again written the formula here for better understanding. So now I have to calculate m of 1 3, then I will calculate m of 2 4. Actually it is a bottom up approach, I told in my first class lecture. Then principal diagonal, next level, then so on. We will move on towards the top, bottom to top. Okay, so m of 1 3 calculated, then we will go for m of 2 4. So yes, I'm sorry, I have not calculated. M of 1 3 needs to be calculated, then I will go for m of 2 4. So when it is m of 1 3, I is 1, j is 3. First of all, you have to calculate the probable value of k, for which you are going to apply this formula actually. So this formula will be evaluated based on the different values of k, and you have to find out which one is the minimum one. So I1 J3. So k starts from I and repeat up to j minus 1. Here I is 1, so k starts from 1 and repeat up to j minus 1. That means 3 minus 1 equals to 2. So 1, 2, 2. So there are two k values. One is 1 and second one is 2. So apply 1 here. So the formula is m of ik plus m of k plus 1 comma j plus this one. So when k equals to 1, it is actually m of 1 1, because I1 k1, m of 1 1 plus m of k plus 1 comma j. K plus 1 means 1 plus 1 2 comma j means 3 plus p of I minus 1, that is p of 0, into p of k, that is p of 1, into p of j, that is p of 3. So m of 1 1 is 0, because principal diagonal is 0 here, and we have already calculated. We are reusing it. We are not recalculating, we are reusing the value. M of 2 3, it is already done. M of 2 3 was 1000. Fine. So we have put the value here, and we have to calculate this part, that is p0 into p1 into p3. So p0 you know it is 10, p1 you know it is 20, and p3 you know it is 1. So put the value here. So 10 into 20 into 1, so it is by calculation it is 1200. Now we go for applying second k value in the formula, then we will compare which one is the minimum. So m of 1 3 for k equals to 2. So m of ik, that is 1 to 2, plus m of k plus 1 comma j, that is 2 plus 1 3, j is 3, so m of 3 3 plus p of I minus 1, that is p0, p of k, that is p2, p of j, that is p3. M of 1 2 is already calculated and stored into the table, which is 10,000. Then m of 3 through 3 means it is 0, another one of the principal diagonals value, and plus the last one is p0 into p2 into p3. As per the data it is 10 into 15 to 1, so the value is 10,500. So comparing these two, m of 1 3 for k equals to 1 and m of 1 3 for k equals to 2, I found 1200 is the minimum one, so that should be stored at m of 1 3, because minimum cost is the main consideration here. So as m of 1 3 for k equals to 1 gives the minimum cost, hence we have to store 1200 at m of 1 3, and we will store the appropriate k value, which is k equals to 1, for which you have got 1200 as the minimum value at s of 1 3. So s of 1 3 will receive that k value for which you are getting the optimal cost here. So 1200 is the value of m of 1 3 and s of 1 3 is 1. Okay, so we have stored here 1200 and s of 1 3 is 1. Now we will go for m of 2 4, and similarly we have to fill up s of 2 4. Okay, so now we go for m of 2 4. Okay, I have written it, I have noted all the data here. So m of 2 4 means I1 J4, I'm sorry, I2 J4, sorry. So now first of all calculate k. K will be from I to j minus 1. As I is 2, j is 4, so k starts from 2 and repeat up to 4 minus 1, that is 3. So 2 to 3 is the range of k. So there are two values, one is 2 and second one is 3. So for calculating m of 2 4, you first have to apply k equals to 2 in the formula. The formula is m of ik plus m of k plus 1j plus p of I minus 1 into p of k into p of j. So m of ik, I is 2, k is 2, m of 2 2 plus m of k plus 1 comma j. M of k plus 1 means m of 2 plus 1 3 comma j means 4, m of 3 4 plus pi minus 1, that is p2 minus 1 p1 into p of k, that is p of 2 into p of j, that is p of 4. So m of 2 2 it is 0 from the table already calculated. M of 3 4 you have already calculated, that was 5000, plus p1 into p2 into p4. P1 is 20, p2 is 50 and p4 is 100. So multiply these three, we finally got the value 105000. A big value. There is no chance of getting it as a minimum as per the data is concerned. So now apply k equals to 3 in the formula. So I to k, that is 2 to 3, plus k plus 1 to j, that is 4 to 4. Then pi minus 1, that is p1 into pk, that is p3 into pj, that is p4. So m of 2 3 we have already calculated. M of 2 3, yes, it was 1000 Yeah, 1000 plus m of 4, you know the principal diagonal 0 plus p1 into p3 into p4 as per the data we have calculated, it is 3000. So comparing these two, this is a very big value, this is a very small value, so this one is a minimum one. So m of 24 will get 3000 as a value, m of 24 will get 3000 as a value, and at the same time s of 24 will receive 3, the appropriate k value for which you get the minimum one for m of ij. So 3000 is obtained for applying k equals to 3. So s of 24 will receive that k value which is 3. So s of 24 receives 3. So only one cell left, that is m of 14 you have to calculate now. So m of 14, I1 J4. So first of all calculate the range of k. K starts from I and repeat up to j minus 1. Current I is 1, current j is 4. So 1 to j minus 1, that is 1 to 4 minus 1, that is 1 to 3. So k have 3 values, k equals to 1, k equals to 2, k equals to 3, because the range is 1 up to 3. That means 1, then 2, then 3. So in the formula, in the same formula which you have applied for calculating m of 24 or like, the same formula needs to be applied here. So for k equals to 1, m of 14 you have to get the value, you have to calculate the value for m of 14 for k equals to 2, and at the same time you have to apply k equals to 3 in the formula, and you have to calculate m of 14 here. So m of 14 when k equals to 1, the formula again I am repeating, that is m of I to k, that is 1 to 1, plus m of k plus 1 up to j, that is 2 to 4, plus p of I minus 1, that is p0, p of k, that is p1, into p of j, that is p4. Putting the value you get 23,000 as a result. Then second k value needs to be applied. For k equals to 2 you get 15,500. For k equals to 3 you are getting the minimum one, 2200. So definitely m of 14 will receive 2200 as a value, 2200 as a value. For k equals to 3 you have obtained it. So s of 14 will receive that k value which is 3. So s of 14 receives k equals to 3. So almost we are at the end of the solution. So the last part is very simple. We know that m of 14, that is 2200, is the minimum scalar multiplications for this problem. So your one of the answers has come out, that is your minimum number of scalar multiplication is 2200, because whenever you are getting the value for m of 14, so actually you are considering the full chain P, Q, R, S, P to S, 4 matrices in the chain, 1 up to 4, first to 4. First matrix, second matrix, third matrix, fourth matrix. So entire chain is complete. I told in my dynamic programming lecture for matrix chain multiplication formula derivation, there I have told that the last cell which will be filled up, that is m of 1, 4 here, that means actually m of 1 n is 4 here, total number of matrices. This cell will finally give you the minimum number of scalar multiplication value. Okay, so be careful. So 2200 is the answer, minimum number of scalar multiplication for solving this chain. So now considering this one, again we have to calculate what is the exact parenthesis sequence for it. So we have to construct a table here, and I told in my last lecture that you have to use S, that means use S table for parenthesization, and S table identify the row and column number of the S table, that means row index and column index of the S table where you have stored the last k value. That means we have computed m of 14 at last, so definitely S of 14 is the last cell where we have stored the last optimum k value, that means that k value for which you have got the optimum result for m of ij. So that's why I have highlighted these two indexes. Okay, because it is required for getting the parenthesized sequence. So actually we will call this recursive definition for parenthesization. We will call S table, we will call two indexes I and j, that is row and column index, and this I and j starts from 1 and n. N will be the total number of matrices, here it is 4. So we have to call two indexes for the initiation of this call, when I will be always 1, because row index of both the matrices will start from 1, because here we are considering only S matrix. So the first row I, because first row 4th column or first row nth column will hold the last k value, so you have to initiate this call from 1n. So here 1 4. So when I not equals to j criteria holds, then it will have two recursive calls. One is s comma I comma s of ij, that means entry at jth column under ith row. Then second call will be s, that means you have to use s table, comma s of ij, which you have used here, plus 1 comma j. It is not j plus 1, s of ij, that is entry present at jth column under ith row of s table, plus 1 comma j. So I told, first of all you have to call I equals to 1 and j should be total number of matrices. That's why 1 4 here. If it is 5 matrices in the chain, that would be 1 5 here. Next column will be the last one. Similarly, m of 1 5 will be the optimum value. So we start from s of 1 comma 4. So I1 j4, I not equals to j satisfies. So the first call as per the definition, s comma I means 1 comma s of ij, that means s of 1 4, s comma s of 1 4 plus 1 comma j. Okay, so take the value from the table, s comma 1 comma s of 1 4, s of 1 4 is 3, so s comma 1 comma 3 comma second one is s comma s of 1 4 plus 1, s of 1 4 I have identified it is 3, so 3 plus 1, so 4, so 4 comma 4. So when I and j are similar, that means no further call is expected from here, because here I is 1 and I is 4 and j is 4 also, they are same. So this implies in this chain you have total 4 matrices, p, q, r and s. This is visible here, p, q, r and s. So 1 comma 3 means from the first matrix up to third matrix there will be a parenthesis, and 4 to 4 means fourth matrix alone, that means from 1 to 3 in one side and fourth one is another side. So here again you have to go for further call, that means you can go for further call from this result. Here s comma 1 comma 3 means this is I, this is j, because you know as per the recursion concept is concerned, recursive call from the next time onwards will be acted upon the small r inputs. Here it was earlier 1 4, now it is 1 3. Okay, so here I1 j3, again I not equal j, so this definition satisfies. S comma current I comma s of ij means s of 1 3, s comma s of 1 3 plus 1 comma j. So what is s of 1 3? S of 1 3, it is 1, so put here. So as it is 1, so definitely this should be 1 plus 1 2, so the call is 1 to 1 2 to 3. So 1 to 1 means take this one for further parenthesization. So 1 to 1 means p alone. Okay, 2 to 3 means q to r, second to third there is a parenthesis. You may write p alone, p must be included within a pair of parentheses, but here I have not included it because I have shown only the boundaries 2 to 3, so 2 and 3 are parenthesized. Okay, so 1 to 1, that means first matrix one side, second and third are clubbed together, so this is the result. Then it is I, it is j. So 1 to 1 means there is no further splitting required. 2 to 3, this is I, this is j. Again you can explore the formula, take the value from the table. You will find here it is 2 to 2 and it is 3 to 3. So that means q alone parenthesized, r alone parenthesized. You may do it, you may not do it, but if you do it you can understand the single matrix in a chain, the condition for. That means when a chain consists of only one matrix, you have filled up 0 in the principal diagonal. So you can understand it, the necessity of it. So in this manner you can write p within parentheses also, but they don't have any effect. Similarly s can be enclosed within parentheses, there will be no effect, because the boundary indicates that q into r to be multiplied first, then you have to come to P, then P multiplied with the intermediate result, then the entire intermediate result must be multiplied with S. This is the way that you have to go for multiplication so that you can get the optimal cost. Okay, so you may verify it. So it is the final result. So you may verify it. That means Q into R must be done in first. Verify it means if you put the dimension and find out the scalar multiplications, you have to verify whether 2200 is the result or not. So let me verify it. You can alone verify it, there would be no issue. So it is P 10 into 20, 20 into 50 for Q, 50 into 1 for R, and 1 into 100 for S. So Q into R to be done at first. Q into R to be done at first means 20 into 50, 50 into 1. This part should be done in first. Okay, so this part is done in first means the resultant matrix for Q into R will be 20 into 1. But the scalar multiplication will be 20 into 50 into 1. That means 20 into 50 into 1 means 100,000. Okay, then take P. P is 10 into 20 and Q into R gives the product 20 into 1. So P into the product is actually 10 into 20, that is P, and here it is 20 into 1. So ultimately P into this product will be 10 into 1, and their scalar multiplication will be 10 into 20 into 1, that is 200. Earlier it was 1000, it is 200, so it is accumulating this 2, it is 1200. So now the product of these three is 10 into 1. So 10 into 1, S is 1 into 100. So final will be 10 into 100. So dimension wise, but the scalar multiplication will be 10 into 1 into 100, that is 1000. Earlier result was 1200 plus 1000. So adding these two, you will get 2200 as a result, which is 2200 stored into M of ij. So your result is perfect. Your parenthesization is also perfect. Okay, you can verify it. So that I have mentioned in my last lecture also. So in this way you can go for matrix chain multiplication problem solution. Thank you.